Hi, let us begin this tutorial with the core of all things, that is, what is AI? So in the next few minutes, I will talk about what AI is and what it has to do with ethics. Clearly, very immediately, a disclaimer, we do not have the answer of what AI is. We do not have the definition of AI. For all the reasons that have been discussed for the last perhaps 70 years, AI is a very difficult thing to define. But what I'm looking into is, what do we do when we do AI today, when we research it, when we implement it, when we innovate with it, when we apply it, and how does that lead to the ethical concerns that we have? Now, of course, this is a complex question. It is a complex argument, and I just take a stab at it. But don't worry, I will use a lot of anecdata in my argumentation when I'm addressing it. I start by looking at two AI definitions. Now, of course, as I already said, all AI definitions are wrong, but some are somewhat useful, and these two are useful to our goal here, that is tracing our approach to AI to the ethical concerns of AI that we have today. As per Paul and Mackworth in their book, artificial intelligence, or AI, is the field that studies the synthesis and analysis of computational agents that act intelligently. So this is what we want to accomplish when we're actually doing AI. We want to accomplish that the creation of artificial computational agents. An agent, of course, here is an entity that acts in an environment, whereas a computational agent is an agent whose decisions about its actions can be explained in terms of computation. In contrast to this definition of Paul and Mackworth, we have the definition of Bellman from 1978, which says that artificial intelligence is the field that is concerned with the automation of activities that we associate with human thinking, AI cognitive activities. So we are not actually AI is not about building computational agents directly, but it is about understanding how somebody can act, can do cognitive activities. Something that is a computer program can emulate or execute what is typically done by cognitive activities of people. And I find that this definition of Bellman actually is the approach that that AI has. We are looking into specific tasks such as learning, such as knowledge representation, such as, for example, vision, interaction, right? And each of these tasks has become a separate field in AI that is concerned specifically with automating the task that it is built around from. Now, we can have automation with AI. In fact, we have had automation with AI for a very long time. This is the automation of movement. Technology has been used to automate tasks since I recently learned that the first autopilot, in fact, has been in existence since 1913, something like this. These are two cute pictures of how automation of movement is executed. The specific type of automation we're so the answer is that we take a movement that we want to automate, we decompose it into these atomic movements, that atomic positions that can be done, and then when all of these movements are done together, we get this particularly complex movement. So for instance, if I want to make a robotic arm that does something like that, I decompose that into 6 atomic movements and then execute these atomic movements in sequence, and the result then is this complicated movement that was too complicated for me to repeat right now. Now, the thing is that we take exactly the same approach when we are automating cognitive tasks. So do we do the same? We separate reasoning from knowledge representation, from interaction, from learning, right? And we automate them in isolation. And somewhere there is this hope that somehow this will result in a computational agent. Or do we even care? The thing is, we know that movement is decomposable, but are cognitive tasks decomposable? And the answer here is, if they are, we do not know where to decompose properly. This is established. We are just taking a stab and trying to, like, okay, build machine learning, build automated reasoning, but what part we automate and what part that we do not automate is is not decided based on our understanding of cognitive tasks. So to illustrate this, I take one cognitive task and I show you how we automate it in AI today. The task I picked is reasoning because it is close to my field of expertise, but it is also somehow the cognitive task that is most associated perhaps with intelligence. So there are three types of reasoning. And all of them are basically using a process of connecting cause and effect by using some rules. If we are given some facts and some rules and we want to find answers that are entailed by these facts, then what we are talking about deduction is called deduction, and deduction is something that we automate. So we have we are seeking how to execute automated deduction. So good old-fashioned AI focused on deductions. You can think Prolog. Prolog was built to do deductions, given a set of facts and a set of rules. What can I conclude to hold in this world of facts and rules? If we are instead given some desired state, oops, there it is, deduction. If we are given some desired state of the world, and then some rules that we know hold, and we want to know what has caused this state, what are the reasons why we are observing these effects, how is this state possible, we need to use abductive reasoning or abduction. Now, abduction is sometimes not really seen as separate as deduction, perhaps, particularly for automation purposes. But the difference is that in abduction, you may not be able to identify clearly the causes, but you're looking to narrow down possible causes rather than figure out what exactly the causes is. Whereas in deduction, we are very clear what it can be, what is deduced. There is no like possible deductions, but exact deductions. Now, when it comes to automated reasoning, abduction is most typically associated with answer set programming, and answer set programming has been put forward as a means to automate abduction. Lastly, let's say that we have observed some phenomena, some things that we have deduced are causes or concluded or figured out there are causes, and some things we have figured out that are effects. And we would like to know how are they connected, which rules connect causes with effects. And figuring this out involves a reasoning process which is called inductive reasoning. And this is what supervised machine learning and reinforcement learning specifically are trying to accomplish. They're trying to automate inductions. Now, because of this cognitive splintering, you see, even if taking something like reasoning, we are splitting it further, we are narrowing it down and say, well, reasoning is connecting causes and effects with some rules. And then we say, well, there are these three types of reasoning, and then we are automating all of these three types of reasoning using different AI methods. So when we do that, things can go wrong. Things can go wrong because we do not know where to splinter the cognitive tasks, how to do it well. And this does not necessarily have to do anything with ethics, but it might. So just very quickly, what can go wrong as a direct result of how we have chosen to automate deduction, abduction, and induction. When we use deduction, it is important that all the rules that are required are specified. So deduction deduction is only made on the rules that we have explicitly provided to the system that does deduction. Not even the most obvious or commonly known rule must be forgotten. This is a very big problem. It's like, what is it that you have forgotten to thought about? To show how easy it is to forget to enlist the obvious, I will use a puzzle. So there's this puzzle in which we have information that George is looking at Jane, Jane is looking at Jack, George is married, Jack is not married, and we are trying to deduce whether there is a married person that is looking at unmarried person. Now, people can do this very easily. You can actually very easily do it in Prolog as well, as long as you remember to explicitly specify what we know to be true about the world, that a person is either married or unmarried, that it is either in this state or the other. There cannot be a person who is neither married or unmarried, or both married and unmarried at the same time. And we take this to be fact of the world, okay, except maybe at 2 a.m. in some bar somewhere, but this needs to be explicitly given to Prolog, if you like, so that you can make the deduction that yes, there is a married person that is looking at an unmarried person. When we are talking about abduction, we can have more than one cause that have the same effect, and we may not have enough rules to choose the right one. So I have two Sudoku puzzles as an example of abductive reasoning that one can do. The left puzzle is solvable, so there is only exactly one combination of numbers that you can put into the fields to solve the puzzle, but the right puzzle is not solvable. There is more than one possible solution here. Now, the problem with abduction here is that when people are doing abduction, when Sherlock Holmes is doing abduction, he typically goes and asks additional questions and runs experiments and can use these findings to eliminate some of the possible causes. But when we are automating abduction, even if there is something that is very clear that can be eliminated, right? This information, again, as in deduction, has to be explicitly, specifically given when the program, if this is an answer set program, when the answer set program is written down, right? Not when the system is implemented. In induction, the problem is that induction, the way it is being done now in supervised machine learning and reinforcement learning, always discovers correlations between phenomena, correlations between causes and effects, and not actually causation. We have a bit of a same situation in induction as we do in abduction. In fact, when people are trying to figure out what rules connect a cause and effect, they can make a hypothesis, they can identify some correlation between causes and effects, and then they can run additional experiments to test whether indeed this is a correlation or causation, right? But when we do it induction through machine learning or to reinforcement learning, this option simply does not exist. The problem, of course, with correlations not being causations is that there are many things that are correlated, but there is no causal link between them. This is an example from the website that collects these curious, spurious correlations that obviously don't have correlations, that are not causations, right? And how good your inference rules are, your correlations, in fact, even are, depends very much on which examples you have taken to work with. So we are limited to the causes and effects that are provided to the system that is automating induction. There is always, of course, the danger that an example is rare, but it is there. It should be. It basically changes the rule. It would nullify your inference when it is omitted from the data set, but you simply do not have it in your data set, and there is no way to, well, it's very difficult to actually predict what it is that you're missing. So in all of these cases, one can actually say there are basically two problems. The first problem is that you have to think in advance of everything, and you have to be vigilant and figure out what it is that you're not thinking about. And the second thing is that the system works with information that it is provided. It does not really have possibility to ask for additional information and to look for additional information. This is the limitation of the core ways in which these systems of automated reasoning are built and work. So if you are paying attention, you will see that what automated reasoning does is takes causes and rules, or takes effects and rules, or takes causes and effects and deduces rules. But where do these causes and effects and rules come from? What parts are actually, so what we automate is the reasoning process, but where does the input to this reasoning process come from? What happens to the unautomated parts of a task? If I zoom out of this reasoning picture, I will find that there is more to reasoning than reasoning. So we frame the problem for automated reasoning very cleanly. For machine learning, this is a data set of examples and labels, for example. For deduction, this is a bunch of facts and rules. But how do we get to this clean reasoning problem? The answer is a lot of human labor, obviously. We need observations. So let me just guide the pointer here. We need observations to identify what is relevant and what is not relevant to be considered as cause. And of course, we need some way to represent these causes in some kind of a formal language, be it a data set, be it a knowledge base, but a person needs to do that. we need then to interpret the computer-generated answers, so again, and enact perhaps if these are actions, maybe we need to enact these actions. So a chess player AI needs somebody to move the pieces around the board. It may not necessarily move its pieces by itself. And most importantly, we need rules. If we are doing abduction or deduction, we need to know what the rules are that we can use. And the only way to get these is to consult domain experts, which then can identify rules and then can be trusted to think about everything that needs to be thought about in this situation. And automating each of these additional cognitive tasks is a separate sub area of research in AI. And a lot of these tasks we still can't automate, and we have people that are doing them. So there's a little bit of automation, humans binding, automation, human binding. In the past, I have to mention here that this point that all of these people were experts. And in fact, all of the AI solutions that were being developed before the first and the second AI winter were aimed to be used by experts. So it was known before a system is developed and deployed who it is exactly that will be using this system, who it is that will be developing it, who it is that we will be using it. Today, we can have anyone involved in representation of examples. In fact, the big win of machine learning can be seen as getting rid of these very expensive experts for knowledge representation and replacing them with lay people who can all very clearly identify whether the picture has a cat in it or not. But furthermore, we can have anybody actually use an AI system. You can have anyone download a neural network, download the data set, train the neural network with the data set, boom, you have a prediction model. And these people who are using AI today, we don't know what they know necessarily. So it could be that they don't know that there is a difference between correlation and causation, and that they are using correlations where you really need to make sure that what you're using are rules that are causal rules. So AI has become something that was a tool for experts, and from being a tool for experts, it has become basically a member of our society. So we don't common people interact with AI. So this is lights off at my office. Sorry about that. And we don't necessarily know what they know. We cannot make sure that they will think of everything. So here comes the ethical considerations of AI. So why AI ethics? Because we build systems that interact with the world of people freely, openly. But these systems that we build are not really agents. They are just automations of some cognitive tasks, right? But they have agency, right? So they are used in systems. So machine learning or knowledge representation or multi-agent system interaction is used as part of a larger system that does something, right? It replaces people in doing some tasks. So how do we make sure that the sum of all parts here, both the automated parts of cognitive tasks and the human executed parts of cognitive tasks have, if not neutral, then if not positive, then at least neutral ethical impact? Now, at this point, before concluding, I have to bring something to your attention. Typically, when we are talking about AI ethics, what people have in mind are Terminators and deep fakes and trolley problems, dilemmas, and then AI ethics somehow boils down to the problem of what should the self-driving car do in an ethically questionable, morally difficult situation. This is an example from the Moral Machines project. If you are the last person on earth who hasn't tried it out, by all means, go ahead and be entertained. The link is down below on the slide. So the trolley problem here is the choice between should these driverless cars whose brakes have failed and has 4 passengers run over 5 pedestrians. And you can see there is a difference between the pedestrians. Some are old, some are children. Or should it instead run into an embankment and thus end the life of the passengers, possibly owners, definitely users of its system? It is very important to be vigilant that this is not our problem. This is not the problem of AI ethics. Moral Machines uses these little ethical dilemmas for purposes, but the purpose of AI ethics is not to figure out this brilliant device that somehow solves these problems that moral philosophers recognize really do not have solutions. Now, what is the subject of AI ethics is the following example. An example that can be encountered all over the world, I believe. You have your local place that sells you cheap coffee that you desperately depend on in the morning, and this coffee machine requires self-service, so people come and then touch the button and then order the coffee. However, we are now into the pandemics. This is why we are not in Japan, sad. And we do not necessarily want a bunch of people touching the same buttons, right? This is unhygienic, and it is possibly a vector for transmission of the disease. So we do have the means. Should we update these machines to voice recognition? Should we have in them a voice recognition system that a person can walk up to and say, this type of coffee, that type of coffee, this much sugar, that much sugar? This is our machine ethics problem, because you need to realize that at this point, what you're doing is you're changing something that was performed by people into something that is being performed by machine, that there is a severe asymmetry of knowledge of what is going on and what is involved when you're building such a system, that in order for a voice recognition system to work, there needs to be a microphone that listens to and records conversations around it, right? And that this is data, and that this data is stored somewhere, and then it is accessed by some people, and it is used by other people for other means. And then you have to make sure that everybody that gets in touch with this machine is actually aware of what is happening with this data. Then you have to make sure that nothing bad can happen with this data afterwards, after it has served its purpose of getting a person to a cup of coffee. So this is what AI ethics is actually about. This is a very good representative problem, not the Turing problem dilemma. In the next set of slides, I talk about what is the landscape of AI ethics today, and specifically what is the role and position that machine ethics has in this landscape.